So what I'd like to do today is, before we get to our main point of our lesson, I want to take a look at some things from yesterday, some patterns or things that maybe we saw that will always be true. So one thing I want to start with is an original graph. So when f of x is, let's start with increasing, right? That's one of the behaviors our graph can have. When a graph is increasing, what can we say about its slope? We can say the slope is always positive, right? If a graph is going uphill, its tangent line is going uphill. And for a function to be positive, that means it's above the x-axis. Okay, so when a function is increasing, its derivative is above the x-axis. Likewise, if a graph is decreasing, we can say its derivative, its slope is negative, negative meaning below the x-axis. So if a graph is not increasing or decreasing, it could be doing one of two things. It could be standing still, which we would say is a smooth max, min, or shelf. I'm going to introduce this word shelf here. We know what a maximum is. I'm going to come over here to the left. A maximum, the graph goes up, turns around nice and smooth, comes back down. A minimum goes down, turns around, comes back up, the slope, or a shelf is when you kind of have a combination, right? You go up almost like you're going to have a maximum, but then you don't change direction, you just keep going. That's what we would call a shelf. It's a stationary point in the graph. The graph is not increasing or decreasing there. So when f of x has a smooth, max, min, or shelf, the slope would be 0. And if a graph is 0, that means it's on the x-axis, right? It's an x-intercept. Okay. So a graph can either be increasing or decreasing or stationary, meaning it's neither decreasing nor increasing, or it could have a cusp, a corner, a vertical tangent, or any sort of discontinuity. So if our graph has any of those things, the derivative does not exist, right? That's that whole concept of differentiability. And so what we can do is we can use this to speed up our process from yesterday. So instead of looking at specific points and thinking about using the spaghetti and calculating the slope, we're going to really just look for these 4 key things. This first graph, it says here's the graph of f, sketch its derivative. I'm going to try to keep the colors the same by looking to see where this graph is increasing. Because where this is increasing, my derivative will be above the x-axis. When my graph is decreasing, I didn't pick great colors here, but when my graph is decreasing, my derivative will be below the x-axis. Meaning, when my graph has a smooth max, min, or shelf, we're going to be on the x-axis. So max or min, max, min. So it looks like we're going to be on the x-axis. Let's call it like -3. Let's call it 0-ish. And how about +3? So I started with my max mins. And now I'm going to connect those max and mins. Right? My graph is decreasing, so my derivative is negative. My graph is increasing between this point and this point, so my derivative is positive. I still have to connect those 2 points. I just know I want to be above the x-axis. My graph is decreasing again, so to get from here to here, I want to be below the x-axis. And then my graph is increasing, so I want my derivative to be above the x-axis. Now, one thing I did a little bit differently on this side is this kind of started to flatten out again, so I kind of, started to turn back up towards 0. But so again, decreasing becomes below, increasing above, decreasing below, increasing above. So it just speeds up our process a little bit. Let's take a look at this one. Same idea. Here's a graph of f. Let's sketch its derivative. So again, I'm looking to see where this graph has any max-mins or shelves, which it does not. I'm going to say, well, this graph is increasing here. My graph is decreasing over here. So I want to be below the x-axis. On the left side of 0. I'm going to be above the x-axis on the right side of 0. And now maybe I will think a little bit about that spaghetti idea. Right? If I were to think about that spaghetti, a tangent line out here is really, really, really shallow, really close to 0, but below. And then maybe in here it starts to get a little bit bigger, like -1, -2. And just to the left here, if I were to lay down a piece of spaghetti, it has a negative slope, but it is really, really, really steep. So it almost looks like that piece didn't really change much at all. Okay. My right side, same concept, right? Symmetry, let's use it. So just on the right, it's really steep, but it's positive. And then a slope of about 1 or 2. And then out there at the end, it's really close to 0. And we'll just connect those points. So in this case, I used a couple of slopes, but I really had an idea first of where my graph would live. Okay. Good. All right. Let's take a look at this one. Given the graph of the derivative, sketch a possible graph of f. So we're changing the directions here. First of all, I want to point this word out. We'll come back to this because we may all have some slightly different graphs, and that is okay. We'll talk about why. So now we have the derivative. Let's label this. This is f prime of x. And remember, f prime means slope. So they're giving us, and they want us to graph the original. I'm going to slide us back over here. The last two graphs we did, we said, well, all right, we have f, so let's look for these behaviors and then draw these behaviors. Well, now we're going to have f prime, so let's look for these behaviors so we know what the original is doing. I'm going to try to use those same colors. When my derivative is positive, when my derivative is positive or above the x-axis, my original is increasing. Okay? This is my derivative. It is above the x-axis. I'm just shading over it in red, which means my original is increasing until I get to 2. My derivative is above the x-axis, so my original is increasing. Then my derivative is below the x-axis, and when my derivative is below, that means my original is decreasing. Look at this. This is a 0, right? When our derivative is 0 or on the x-axis, that means our original has a smooth max, min, or shelf. I'm just going to kind of notate that here. This is a max, a min, or a shelf. Now, we don't have to decide which one it's going to naturally occur for us. I'm going to take my pencil here. I'm going to draw a graph that is increasing and then decreasing, and it has to have a smooth transition at 2. So let's increase, and then let's decrease. Look at that. At x equals 2, when I changed from increasing to decreasing, that maximum naturally occurred for us. Okay. Now, some of you may say, "Ooh, mine doesn't look like that, Mrs. Patton. Mine, is down here, or my maximum is here, or my maximum is here." That's okay. We could have a lot of different graphs. Remember this keyword being possible? So maybe your graph looks something like this. Right? The good news is we all still have our maximum when x equals 2. We're all still increasing and decreasing. Our steepness is a little bit different. That's okay. I purposely left a scale off of our y-axis. Okay? Think about this for a moment. This is like an upside down parabola. What if my original was negative x squared plus 6? When I take its derivative, I just get negative 2x, right? I'm going backwards because my derivative is on the left, right? So this is a line, it's going downhill, negative 2x. My y-intercept is off, that's okay. Well, maybe yours was more like y equals negative x squared plus 2. Well, what's its derivative? Y prime equals negative 2x, right? Whether our vertex is at a 6 or at a 2, or maybe our vertex is even down here at negative 5, it doesn't matter. Because when you take the derivative of a constant, it goes away. So if we are going this way, if we have the derivative and we're trying to find the original, we may never know what that constant should be. Right? So when we talk about a possible sketch of f, we're going to be missing this vertical movement, this vertical shift. That's okay. That's why they're going to tell us a possible graph. So that means our graph could be moved vertically. For alternate solutions. Okay. All right, let's flip it over. Same idea. It says, given the graph of the derivative, sketch a possible graph of f. So without making you dizzy and me flipping our paper to derivative is above the x-axis. Our original is increasing. So I'm above the x-axis from negative 4 to 4. So I'm just going to kind of jot that down over here. My derivative is below the x-axis to the left. So we're going to be decreasing to the left of negative 4. It is also below the x-axis to the right of positive 4. And we are on the x-axis at positive or negative. And those will just turn out to be what they're supposed to be. We don't have to make that happen. Lightly with my pencil, remember we're decreasing, then we're increasing, then we're decreasing again. Just very lightly with my pencil. So we see that this is going to be a minimum. We're going to smooth it out. We see that this is going to be a maximum. So we're just going to come in now with our pen. You may be way up here. You may be way down here. It may be steeper than mine. That's okay. So I want to have a minimum at negative 4. I'm going to turn around and have a maximum at positive 4. And there's a possible graph. Mine went almost through the origin. There's nothing telling us that we have to do that. Okay. All right. I'd like to go ahead and pause it and see what you can do on your own here. Same idea. So if you want to hang out with me and do it, that's fine. If you want to pause it and see what you can do on your own, I think that's a great idea. So again, when my derivative is above the x-axis, my original is increasing. So let's say from negative 5 to 0, and then from 0 to 5. Notice I stopped at 0 though, because my graph is on the x-axis there. So I'm increasing, and then I'm still increasing. My derivative is negative to the left, so we're decreasing to the left of negative 5. My derivative is negative to the right of positive 5. Remember, before we do anything else, when our derivative is on the x-axis, that's when we have a max, a min, or a shelf. And it will be naturally occurring for us. So I want to decrease until I get to negative 5. I'm going to increase until I get to 5. and I'm going to decrease again. So just very lightly with my pencil, I'm just kind of getting the direction changes in. I need to have a max, a min, or a shelf here. Well, look, it just so happens to be a min. Here, I need a max, a min, or a shelf. It just so happened to be a max. But remember, we can't ignore this. This is where we're going to get a shelf because it's not a max or a min. There's no direction change there, but the slope equals 0. So we have to flatten our graph out at x equals 0. So we're going to make that minimum occur. And then when I get to x equals 0, I'm going to flatten out, get that shelf, almost like I'm getting ready to turn around and come back down, but instead of turning around, I'm going to continue going up. And then don't forget to stop and turn around at x equals positive 5. Okay, so we have a minimum. We have a shelf, right? It's almost like a horizontal, well, it is a horizontal tangent, right? And then we have a max up here. Okay. Good. And again, your graph might be down lower, might be up a little higher, and that's okay. All right. Last one. It says sketch f of x. Notice it does not say sketch a possible graph of f. It just says sketch f given the following pieces of information. So we've got 3 criteria. Number 1, f of 2 equals 0. Well, they're just telling us that we have the point 2 comma 0. So great. The second piece, f is continuous everywhere. No jumps, no holes, no asymptotes. We want to make sure in the end that our graph is continuous. And then number 3, they're giving us information about f prime. F prime is equal to -3 when x is less than 1. F prime is equal to 2 when x is greater than 1. Well, what does f prime mean? F prime means the slope. So they're telling us the slope is -3 on the left side of x equals 1. Then they're telling us the slope is 2 on the right side of x equals 1. So this is our point at 2. Here's x equals 1. My graph, remember this whole piece is a slope of -3. And on this side, I want the slope to be positive 2. So, 2 things. My graph must be continuous, and it must also pass through this point. Well, if it has to pass through this point, maybe I start there. In this whole section, my slope is 2, and I want to go through that point. So let's start there and go up 2 over 1, up 2 over 1, up 2 over 1. I could also go down 2, left 1, but that gets me to x equals 1, so let's stop there. So there's my right side. That's when x is less than 1, my slope is -3. But remember, I want to connect to this piece because I want to be continuous. So I stopped here. Let's pick up where we left off. And let's go up 3 and left 1, up 3 and left 1, up 3 and left 1. Just missed all those points there. So it's a little steeper on the left than it is on the right. Our graph is continuous. It's not differentiable. That's okay. They did not say that the slope exists at 1. There's no or equals to there. But the reason I did the right side first is so that I ensured that I went through that point.